They're wrong. Wait, optimal points? Maybe it's possible. Yeah. Yeah.
Test 1, 2, 3. Okay. In light of potential power outage in the next couple of days, we will make adjustments necessary with respect to the homework due dates and all that. And in light of potential class cancellation on Thursday, we'll try to do as much as possible today.
No.
Okay. We're going to review the last lecture on PCA, and we're going to see how PCA in action, the eigenphase in computer vision. And then we're going to provide a singular value view of regression, linking OLS, pseudo-inverse, PC, and ridge all together. And the last thing is I want to touch upon the foundations for CCA. Principal component analysis is to maximize projection variance over any chosen axis of projection. What's illustrated here is in the center, I have these red points, okay? These are already zero mean. The center of this point cloud is at the origin. And focus on the middle plot. I have this pie chart looking like graph, and there are multiple radial lines indicating a potential projection axis, okay? And surrounding the center plot, I have a bunch of actual projection based on particular axis. So let's take this as an example, okay? All the red points are identical replica of the center of these points in the center, okay? And in this plot, the axis I'm considering is this is my V, okay? And this corresponds to this line passing through the origin, this projection axis, okay? And now, what does the PCA want? Pick any V. For example, this one. You can see this gray line is parallel to this line. Yeah, the direction is consistent. All the points drop perpendicularly to that line, orthogonal projection. Okay. So each point within that space becomes all these blue points on this line. Okay. Then you can calculate the variance, the spread of these blue points, the blue projections. Okay, so for each of these axes, for example, I choose a different line. For this V, which correspond to this line, right? These are parallel to each other. It corresponds to this line. Okay, I do the same thing. I can see it spreads out like this. When I did this, it spreads out like this. Okay, so every time I do the projection, I will be able to calculate the variance of projection, V of blue points. These are the projections, okay? And for that, so for each of this, I will have a number. I'm gonna, for example, if this is my variance, let's call it, V is used, let's call it alpha. Then for this line, I'm gonna, this is the alpha. I put the point here because this size is proportional to alpha. Okay? So for this line, I get another value. this is a beta, for example. I calculate the variance, the spread over this projection axis. And for this one, it's gonna be this value. From origin to this, the length of this is beta. So for each possible choices in this 360 degrees projection axis, each projection axis, I get a number. So that will help me trace out this curve. That's the blue curve here. And that is my criterion value. Okay, this is Rayleigh quotient. V transpose, X transpose XV divided by V transpose V. When we think about these points as a Gaussian distributed 2D points, we tend to think about ellipse, right? This long axis is aligned with this elongation, and the minor axis aligned with the shorter minor axis. But think about the Rayleigh quotient. The Rayleigh quotient is not the ellipse you might have thought, because it's divided by V transpose V. Okay? And if you look at, now I trace out this dumbbell shape, right? Like a peanut shape of this is my objective value, this curve. And the minimum point is achieved at this direction. That corresponds to this one. Okay? This is the minimum projection variance direction. And this one corresponds to this green line. The green line, in this case, you can see that this line is parallel to this gray line, yeah? And this it spreads out maximally, okay? That's the maximum projection direction. That's my first PCA. And this cyan curve, this is V1, the maximum projection. This is V2, this is minimum projection. They are perpendicular to each other. Any questions about this plot? Yes?
So, what is alpha and beta, the variance of it?
What is this variance? Are you asking about variance of what?
So what's the meaning of alpha and beta?
Oh, it's just the size of the variance. Once all the red points living in 2D projected onto this 1D line, it becomes blue points living on the blue line. And then there's a spread. You can calculate the mean, you can calculate the variance. Take the variance value or plot it as the radius of this peanut shape. Okay? So that is the value of this Rayleigh quotient. Okay? So that's the intuition. So you can see that for this Gaussian distributed points, the first PCA, the direction is aligned with the major axis. The minor axis goes for the least eigenvector, which minimizes the projection variance. Okay? That's the criterion. And PCA can be applied to a number of multiple PCAs, and we have this joint subspace point of view of PCA criteria. Instead of, we can do it by each time identifying one axis. But if we are looking for K PCA, we can think about finding the K subspace. Any subspace forms a projection subspace. Among all the possible K subspaces, the one that gives you the maximum projection variance is the best K PCAs. In this case, I have 3D points. I'm looking for the two PCAs, right? Basically, I'm finding the plane. Finding a plane, if I project all the points, 3D points, to the 2D plane, it will give me this scatter plot, and I can calculate the total variance. For that, I can associate a variance number. I can do the same thing. Instead of just one, project axis direction, now I have to parameterize my space with two bases. But all in all, it's seeking the maximum variance in the projected subspace. And in terms of math, whether you want to do it by sequentially identifying PCAs one by one, you identify the first PCA, project to the subspace. In that space, find the second PCA, and you do it in onion peeling fashion. Or you just find the jointly, all K subspace, find the max one. The math is identical, and in the K space, it's exactly this. You added up all the projection variance subject to the constraints that all the axes are orthogonal to each other, and it can be written in a compact matrix form using the trace operator. This is just a notation change. There's no fancy math involved. PCA, starting from this criterion, we can decompose the data matrix into its SVD. And then the covariance can be expressed using the right singular vectors. The PCA projection axis, we have derived that the first K PCA is simply the top K eigenvectors of the covariance matrix. Because essentially the PCA criterion, the Rayleigh quotient, is with respect to the covariance matrix. Okay, so it's the V is the eigenvector of the covariance matrix. Once we find out the axis of projection, we project the data. You have all these individual instances, you project it to these axes, you get the coefficients. And then we can reconstruct since there's a projection size, and you reconstruct with this basis, because this is orthonormal basis in that space. So essentially you have this times this basis. This becomes the basis vector in the V space. So that is the point that lives in the projected subspace, as we learned in the last lecture, but yet minimum distance to the original point X. We have the dual views of eigendecomposition. The data X is n by d. N is number of instances. D is the dimension of the features, or number of features. The covariance matrix is d by d, so it's the feature-feature similarity. Okay. The Gram matrix is n by n. It's instance times number of instance times number of instance. It encodes instance similarity. They are all related to each other, because if X equals U as V transpose, C is V S square V transpose, and G is U S square U transpose. Now, that has a practical consequence when you actually apply PCA to your data. If D is much less than N, for example, all the point set example I have shown you, I may have 500 points. My dimension is only 2. 2 is way less than 500. In that case, when I need to calculate PCA, I need to solve the eigenvector of the covariance matrix, which is just 2 by 2. By all means, think about this X transpose X. Initially, I have 500 by 2, 500 by 2. And in the end, it only boils down to a 2 by 2 matrix. Of course, I will go for that route. It's easy to do. But what if D is small and N is large? When will that happen? In computer vision, it happens a lot. Let's say I only have 500 images, but each image is 200 by 200. So D is 200 by 200. If you think about RGB, I have to multiply 3 to begin with. So what would that be? It will be 120K. That's my dimension. What is my N? If I have 500 images, N is only 500. Then would you want to go for D by D? The D by D, the covariance matrix, will be 120,000 by 120,000. Okay? And this comes from this highly it's X is M by D, so it's really long, very wide, but short matrix. You feel it, you don't need to inflate it into a 120,000 by 120,000 matrix and then calculate the eigenvectors. So what do? We compute the eigenvector of the gram matrix instead. And then we derive the eigenvector for the covariance. So here's the math that justifies this action. So we know that XX transpose is a gram matrix, right? U is the eigenvector of the gram matrix. That means if by definition of the eigenvector, the gram matrix times U is US squared, okay? S squared is the corresponding eigenvalues. Okay, this just shows that U is eigen of XX transpose, the gram matrix. Now, if I multiply both sides by X transpose, okay? This equation, I multiply both by X transpose and X transpose. Now, the first two becomes a C, covariance matrix. This is X transpose U, and this is X transpose U. I know it's V. Why? Because by definition, if I think of this as a unit, this follows the definition for the eigenvector of X transpose X of covariance matrix, right? That's the definition of eigenvectors. If it's C applied to this vector, it becomes this vector scaled by just scaled. It's invariant subspace. Okay? So that means V is simply, the X transpose U. Now I put a proportion there only because in the SVD decomposition, I assume it's orthonormal. This V by X transpose U is a proper eigenvector. It's just the length is not necessarily equal to 1. But that's easy to do. I calculate my K vectors, I calculate the norm, I divide each element by the norm. Okay? So you see, in order to do the PCA on 500 images, I first calculate the gram matrix, which is 500 by 500. I solve for the first K PCAs. That gives me U 1 to K. Let's say I just need 20 PCAs. And then I just multiply U by X transpose, the original data. That's much easier to do. Any questions? Okay, good. We're going to see it in action later. We have also shown that this two views to PCA. One is this original definition. We want to maximize the projection variance. If I can point X, you pick any axis, you project to it, and this is orthogonal. And or alternatively, I use this to reconstruct a representation of X within my subspace, okay? And the difference between the original and the reconstruction is this error E. And if I use the least square error, it's the sum over E squared. So when I calculate, my criterion is summing all the projection variance, P squared, summing over all the instance. I'm summing over P because each P is a function of X, original X, okay? So I'm summing over that, okay? So if I write out clearly, it should be like that. That's just definition of variance. If I sum over the reconstruction error, that will be any X. When you vary X, you will have E, and you sum this up. Each term of this, I add them together. This is because this is a right angle. This always add up to this X squared. That's the data. That doesn't depend on which axis you choose. That's just the distance of the square, distance of that point to the origin. Okay? So each term, you always have this constancy constraints. So if there's a sum V that maximizes this sum, it must be minimizing this, right? Because variance plus E is constant. So E is constant minus this V. If V is maximum, this is negative that, and this is constant, doesn't matter, so it must be minimum. Okay? So with that, we make a connection to this low rank approximation. If X has this SVD decomposition, according to PCA, the reconstruction, according to the K-PCA, is simply taking the first, by this, and we can show that, you know, you write out X, it's USV transpose, and this is X, this is a V, you project onto this axis, you reconstruct. And this you can show that it simply is the original USV, but with all the singular values beyond K, knock out to be 0. Okay, so this is what TLS does, right? The total least squares. So they are equivalent from this point of view. The difference is though, when we do PCA, we are seeking the projection subspace. Each PCA is an axis where you have maximum projection. You want to be in that space. Well, TLS seeks the normal to the projection subspace. It's just the way it parameterizes is different. But it's looking really the duality. One is looking at the palm, the other is, you know, the backside of the hand. It's equivalent. They're equivalent. So TLS and OS, they are formulated as a regression of X towards Y. So let's try to bring the formulas closer in order to identify the similarities, the connections, you know, where they're the same, where they're different. First of all, for TLS, let's notice each pair of singular vectors are related to each other, as we have already seen, you know, between the eigenvectors for grand matrix and those for the covariance matrix. Let's say M is a matrix with a rank of R, so it can be decomposed into this, you know, USV transpose. If I write it out in the summation form, it's essentially the each outer product between UI, VI, and multiplied by SI. So if I multiply this equation by VK on both sides, this times VK, this times VK, so what do I have? It becomes this, and K is any number between, K is any of this between 1 and R. So if I do this, if K is not the same as I, this will be 0. Only when K equals I, this will survive, and the value will be 1 because it's orthonormal. So then the whole thing becomes just SK, UK. Okay? Which means if I multiply this singular vector VK, I get UK. Okay? Now, so TLS solution, we have seen in the past, we're going to make adjustments to both X and Y. And the TLS solution is, you know, in the end, is this the last residual term. It's the least eigenvector. You have this representation, and we are going to apply this using what we derived here, right? So this is the SKUK, which equals to the original XY, the data matrix, the joint data matrix times VD plus 1. Yes? I'm just applying this equation to this, you know, SKUK. Let K equals the last one, which equals D plus 1 in this case. And the M in this case is my joint data matrix, XY, okay? Now the reconstruction is the joint data matrix plus adjustment. Now, when I represent the adjustment in terms of the original data matrix, it's just some linear combination of the original data matrix. I can extract this common part, and this is just I minus VD plus 1, VD plus 1 transpose. Okay? In a way, if you understand the math, in a way, it's obvious in the sense this is a projector, right? You know, okay. But then the total least square solution, after you made the adjustment, that is for the tilde A, it lives in that the linear space. It must satisfy this times some W and -1 equals 0, right? We are seeking the adjustment so they line perfectly, they're perfectly linearly correlated. And so this equals 0, we plug that equation 18 into it, we have this. And so this shows that this W minus 1 has to be proportional to VD, D plus 1 transpose, okay? This is a projector to it, so essentially, we have gone through this already. But what's of interest to pay attention to is that this is the normal. This is in the XY joint space. I'm going to show you this 2D example where X is just a scalar, Y is also a scalar. So I really just have 2D line fitting problem. This is just a vector, and this vector is proportional. It aligns with the least eigenvector. Okay? On the other hand, for ordinary least square, we are looking for this least square error. And if I write it in terms of, again, the joint 2D data matrix, I have this. If I perform SVD on this, I have this. And U is orthonormal. It doesn't change the length of this vector. So it becomes this. At this point, if S is identity matrix, then this can be gone, and the V transpose is again just a rotation of the coordinates. It won't change. Under that circumstances, W can be anything, so W has to be 0. The minimum normal solution will be W equals 0. The problem is S is not an identity matrix. So what does that mean? It means I have to find W. W is free to move. This, so long as it's proportional to this, I'm good. That's the best solution. This W can is free to move, and it has to minimize this sum. So let's look at the intuition. This 2D line fitting problem. In the TLS, just focus on the red points. That's original data points. And you can see there are 2 blue arrows. These are the ones corresponding to the eigenvectors of the covariance matrix, okay? I have scaled the arrow, the length of it, by the size of the eigenvalue. So you can see, essentially it's an ellipse like this, right? This is a long axis, this is a short axis, okay? According to the derivation, the TLS is looking for this solution. It's proportional to V2, is proportional to this direction, okay? This direction, okay? And you can see that the fitted line, the green line is the TLS solution. It's perpendicular to the long axis and parallel to the short axis. So my W, together with the -1, is parallel to V2. And this vector, this essentially is my W minus 1 vector. This vector is perpendicular to this line, okay? Both TLS and OLS is to minimize the reconstruction error, so it's always parameterized as normal to the hyperplane. On the other hand, for OLS, again, I have this ellipse. Sorry, it's a bad ellipse, but the blue axis are the calculated long axis and short axis, major and minor axis of this point cloud. What does this mean? Okay, first of all, this is just a vector in this 2D plane. It's a joint space. This x is x, this is y in the joint space. This means this vector, the second component, which corresponds to the y component, is -1. So this is fixed. W could take any value. So that means I can take, for example, if I choose this as W -1, I get a line. The line is simply, it will be perpendicular to this. It will be this line, okay? Any point I pick here, it's the normal to this line. And for this line, I will be able to calculate this fitting error. And that obviously is not as good. The best line, if you think about this, S1 is much greater. S1 is much greater than S2. So what you ideally want the projection onto this S1 or S1 to be minimal, right? If you have a choice, you want the projection onto this, what does this give you? This gives you essentially this vector project to the V1 axis. Let's say it's alpha and beta. Alpha is a projection of W -1, project to V1. Beta is W -1, project to V2. It's just re-representing this with V as the coordinate system. But they are weighted differently. This is S1, this is S2. And S1 is probably much greater than S2. And I want to minimize this. If I have to do this intuitively, I want alpha to be as small as possible. Okay? Subject to the constraint, all the possible valid solutions slide along this green line. I can't take any direction. It has to be, the endpoint has to live on the green line. That's what it is. So among all this, finally, the best solution that's discovered is in this black line here, and that corresponds, this perpendicular to this thick black line, this OL solution. Okay? Any questions? So you can see that if I go, they're almost, even this normal, the normal of this is almost aligning with SV2, but not quite, because of this weighted thing. The weight, particularly how it's weighted. Okay? So, to summarize, PCA is identical to TLS. PCA is looking at the parameterization, the basis for the projected subspace. TLS is looking at the normal to that subspace. Both TLS and OLS is looking from the minimum reconstruction error point of view. They are both looking parameterized into normal to the projection subspace. For TLS, it's the best direction is parallel to the least eigenvector. For OLS, the intuition is this: the W is free to move, but it lives on this line. And among all this, pick the one that minimize this criterion. And it's mostly aligned with this, but slightly off. And this corresponds to why is taking this particular form. It's actually minimizing the vertical projection distance. Why vertical? Because it's illustrating this direction is perpendicular to X. I assume X doesn't have any error, doesn't have any noise. I don't want anything residual component in the X space. That's why it's a vertical projection. Okay. So far, PC does not have a generative model, right? We have generative model for OLS, as ML, maximum likelihood estimation over Gaussian, data generation model. And, we have something for ridge where you have a Gaussian prior map estimation using this. So it would be nice to have a generative view about PCA. By itself, it's very hard to come up with something. Essentially, just calculating a subspace with a maximum variation. But there was a approach called a probabilistic PCA. Okay, so what does that mean? Let's assume there's an unknown latent variable z. Okay, it lives in some space k. Essentially, it's going to go for the k PCA. Okay, it's my k-dimensional vector. Okay. And this is like what we have done with all this reparameterization trick. We assume that is well understood. In that space, every point is by itself. It's RID with respect to everything else. There's no correlation among them. Each point is a k-dimensional Gaussian, for example. Okay? Now, so you can think of, in this latent space, unknown to us, it's a well-behaved Gaussian distributed points. I have colored them in such a way so you kind of see the structure as they rotate in the angular direction. The color changes systematically. And given any point, you pick any point, given z, again, this follows the notation convention. If it's a random variable, we use uppercase. For its particular value realization, we use a lowercase. Okay, so don't get confused. X here is a random variable, but given z, it's z transformed by some fixed, linear transformation matrix, which is d by k. It acts upon z. Z is k by 1. Okay, it becomes a point in a d-dimensional space. And so this is what I have. Given any point, you can apply the v times z to it. It becomes a point in this space. Essentially, because it's a Gaussian, I have an isotropic Gaussian. It becomes elongated Gaussian, rotated as well, right? We have seen this before. Any linear transformation, if it's from RID Gaussian, if you're this, it will belongs to this VV transpose, right? The sigma is transformed. Okay, so it's just another Gaussian with this shape. You can see that the coloring preserved. It has some stretching, but other than that, the coloring is still systematic, going from the radial direction, from 0 degree to 360 degree. Okay, but it will be added with some noise. So given this is a noise-free version, just transform version. Unfortunately, our observations will be tainted by some noise. And that gives our observed variable x, and that's what I have. Now if you look at x, the coloring consistency is gone, right? All the points are, there's a jittering from the original position. It's a 2D noise add to it. Now, largely it's going from this direction to this direction. It's from green to blue to magenta to yellow. But if you look carefully, it has lost this, this very precise alignment, color coding scheme. Okay, so this is simply linear transformation added with some additive noise. Given z is fixed, the mean has been transformed. It may add some m to it, but it's of no consequence to us because PCA takes care of does the centering. So we don't need to worry about m for the time being. And this is just some additive RID Gaussian noise. What is our goal? Our goal is, this is observed variable. Okay? We are gonna estimate our transformation starting from this z. This z is fixed. I know that. I know it's just a Gaussian with a standard deviation of 1. I know the behavior of this, even though I don't know which one's which. I know the behavior of this. I only need to, this is this governing transformation I need to learn. But I only have this noisy observations. So the probabilistic point of view is that I want to figure out, I don't know the z, I know how they're related to each other. I'm looking at the joint probability. I'm going to marginalize, integrate this joint probability over z, marginalize it out over z. It's basically, it takes the map point of view. And this can be written using Bayes' rule. It becomes the prior over Z and the conditional probability. Both are Gaussian. If we two Gaussian multiply together and they're conditional independent, then it's just an exponent get added together. In the end, X is just the, VV transpose, the signal variance plus this noise variance. Oh, sorry, this is somehow cut off. But PCA can be understood as the maximum likelihood estimate of the Lilian transform. So essentially, PCA is the limit when sigma goes all the way to 0, PPCA, given X, PPCA is the estimated V. And this thing is essentially sigma goes to 0, the maximum likelihood estimate of V given the data X. Okay? Because once the sigma goes to 0, I have VV transpose. And you can derive the MLE estimate of this. That will become my eigenvector of the covariance matrix. That's what it is. Through this, without going through PCA, it's deterministic. By allowing to be added with some ID noise, it gives us this probabilistic point of view, and we can use MLE to give PCA a meaning. Essentially, the data is generated with a subspace, in the k-dimensional space. Through some linear transformation, that linear transformation is my eigenvector. And I observe the data. The rest is just some noise. That's what it is. PCA is able to recover this V in the sense of maximizing the likelihood this is generated by some underlying Gaussian process through a linear transform. So PCA is intimately related to a Gaussian. If it's Gaussian distributed, it's very easy to understand. The first PCA is the major axis. The second PCA is the second major. If it's 2D case, it's just minor axis. You can apply PCA to any distributed data, and we mentioned that PCA is good for exploratory data analysis. You don't know what distribution follows. When you apply to any data, for example, the sinusoidal wave, if this oscillation is small enough, probably you would like to figure out this, this is just some undulation over this. You probably want to, if I have to represent this, probably the major axis will, if it's the horizontal axis, that will probably be better. But depends on how much you are seeing. The PCA calculated on these red points will be this line instead. Sometimes it may not make sense. So whenever you get PCA of some point cloud, especially for high dimensional data, you don't really know whether it conforms to this. You need to think of, essentially, you assume the data you have in this high dimensional space is sort of a Gaussian blob. It has a mean, some direction has more, some direction has less variance, and the PCA is picking out the maximum direction variance. There's another, case. So if it's not Gaussian distributed, it does something, but whether this is what you want is a second issue you need to be aware of. Another case is when the data is distributed with multiple modes. It's not a Gaussian. Gaussian is just unimode, one bump. If it's a mixture of Gaussian, bunch of bumps, then the PCA may not be meaningful. For example, I have two strips, point cloud. You can think of each, I may be well approximated by elongated ellipse, but I have two of them. If you calculate PCA on this, you don't have the segmentation of these points. Then what you get is in between them. So this will be a major axis. You are essentially modeling this as this Gaussian blob. Okay? And this is a minor axis. Sometimes you think if it seems like if I've given these 2 point clouds wouldn't it be better if I can pick each one out? Okay? This is called independent component analysis. You assume, you know, after you pick out this, they are, you know, probably statistically they are independent of each other. ICA is not is not something we will be able to talk about in this class, but you need to be aware, you know, the distinctions between PCA and ICA, and what PCA is good at and what is bad at. Now let's see some exciting application on PCA. Let's say you have a lot of face images. That's actually the entirety of my data set, okay? I have all these images. They are all faces. If I have to encode one by one, if this image is 100 by 100, each image requires 10,000 pixels. And I only have, let's say, you know, 200 images, okay? This is the case where N is much less than D. First, given the data, first step of PCA, mean centering, yeah? So let's calculate the mean image. Sorry about that. The mean image is essentially, I add all these images together, pixel by pixel, they are all aligned, right? The first dimension is first pixel, the second dimension is second pixel. How I name, you know, whether it's this image, the first and the second, doesn't really matter. That's the thing with the vector, right? There's no particular ordering of the dimensions. So I add all these images and divide it by the number of images, I get this mean image. What do you observe in this mean image? It's pretty symmetrical. No? Symmetry is really related to this, you know, people's perception of beauty. A perfectly symmetrical face is very beautiful. The mean image is pretty beautiful. Okay, but if you look at the individual images, you know, some faces, I mean, they are actually, these faces are already gone through some pre-processing. There are few landmark points. The eye and the point here is aligned there. Otherwise, even worse. But even with that adjustment, you can see some faces tilt a little bit left, some tilt a little bit right. Right? For example, this one is completely, you know, almost, you know, three-quarter view of this. Okay? And you can see sometimes the lighting come from left, sometimes the lighting come from the right. In the mean image, they cancel out, right? It's sort of, this has a little bit of smiley face. So that's like the, you know, in PCA, where the mean locate doesn't matter, right? Remember? The mean image doesn't really matter, but it's good to know what it's like. And you want to subtract every image from this, you know, you subtract the mean image from every image. What does that mean? Each image, subtract this. So if I have, you know, this black pupils here, I'm only calculating, you know, am I more than the average blackness, right? Now, let's look at the standard deviation per pixel, right? I have a stack of images. Each pixel, I have a lot of numbers. I can calculate the mean, that's the mean image. But the stack of image, all these numbers, you know, skewed into this one pixel location, I have a standard deviation. What does that tell you? In the raw feature dimension, how much variance there is at that pixel location, okay? So which pixel are a lot of here? The teeth have a large variation. What does that tell you? Some images, the mouth is probably closed. You don't see them. Some may be open. So it is open and closed, you know, or where they are, you know, there's a lot of variation. The pupil, not so much variation, very small, meaning mostly black, right? And here you can see some shading effect. So we can sort of see there's a lot of variation coming from this side. You know, here this cheek, because of the location 10, it has more or less the same intensity. Okay, so that's that. So if I remember PCA, if every pixel location, every dimension is uncorrelated with each other, right? Remember the case? You know, remember Sam and Rick? If nothing changes, you send the mean image over and say, please don't send me anything anymore. I don't need to know. If the d-axis, they are uncorrelated with each other, decorrelated data, PCA just picking the axis of largest variation. In that case, if they are decorrelated, you'll be picking these, right, the y pixels. But the fact that the faces, you know, these are not, you know, each dimension is not independently varying. It's a particular phase pattern. So they are correlated, they're highly correlated. So you can't just pick, you know, if I have picked 20 PCA, you can't just pick these. They are redundant. You can do much better by synthesize some patterns from these. Okay? So this is calculated so-called eigenfaces. Okay? So you can see this is the first eigenvector, second one, third one, fourth one, all the way ordered like this. What can you tell? The first few eigenvectors tend to, you know, just go for low frequency, low spatial frequency variations, right? For example, this is roughly picking out the left half is dark, the right half is a little lighter, right? And this is more like picking out the shape of the face, you know? And then I have some small, you know, variation here and there, and the more later on, all the frequencies focusing on little details. That's the nature of PCA. It works for any of these matrix. It's going for, you know, the first one, you know, if I only get to represent the image by one PCA, I essentially, any face image is just, you know, a scaled version of that. So essentially, it's just like this face is more or less taken from left side or right side. Okay? But this, what does the PCA, all these values in the PCA mean actually? It means these patterns co-occur so often, I might as well just summarize in one, you know, one direction. These are the most, you know, common co-occurring patterns, and that becomes my first PCA. It's the major subspace. So what you have seen here is 100 eigenfaces. These faces that have this prominence is called eigenfaces, and each eigenface is associated with eigenvalue. If I plot out the value, it has this typical distribution. What does that mean? In terms of low rank reconstruction, if I throw away something beyond that, I don't lose a whole lot, right? These few are really dominating, right? So, you know, up to, you know, 10 or 20, if you look at this, you know, about these 10, 20, these are the ones that capture the major variation. All the rest ones, sometimes it picks out the mouth, sometimes it's picking out the eyes, the right eye, or little details. Okay, in the least square, pixel-wise, least square fitting error, these are just minor variations. Each colored line is the coefficient corresponding to one single image. So each image can project onto this 100 axis. Each projection gives you 100 coefficients, right? So I link them. So you can see you know, I'm recycling the color, but you can see there are a lot of, if I have 200 images, there are 200 lines there. They all have this pattern. The eigenvalue has this drop off, but the coefficients also for the low, the first few, the size of projection is also much larger. The later frequency component just have less energy. Now I have, you know, I have my basis, okay? The original image is close to 100 by 100. These are my origin. What is my reconstruction? These are reconstruction using 100 numbers per image. Okay? Back, forth, back. It's not as sharp, but it has captured the major variations. Think about this. Instead of, 100,000 numbers, I only need to send over 100 numbers. I can have this result. That's a major dimensionality reduction. Okay? Now, this is my original, this is reconstruction, I do the differencing. This is the residual, the reconstruction error. Okay? You see that all that's missing is the details. The sharpness around the eyes, where the contrast happens, smooth areas you have already captured fairly well. This is one working example of PCA. I have this image. I chose this image because, remember, this is a perfect symmetrical mean image. This image is not symmetrical at all, right? It's a profile image. This image equals the mean image plus 1.138 times this first eigenface plus this minus 19.957 times this second PCA, the eigenface, plus 3.162 times this pattern. Okay, the third PCA, so on and so forth. Okay? So you see each PCA is capturing this activation pattern, right? Instead of just going, represent each pixel by themselves, you have this correlation among these pixels and they tend to co-occur together. Why not just capture all of that in one? Okay, you can see the coefficient dies down pretty quickly. Also the size of projection also gets smaller and smaller. As you peel onion one by one, not much to project. And this is estimation. In a way, think about this. How do you evolve from mean to this profile image? And this is the error. Let's do a progressive reconstruction. This is what I was talking about. The mean image is a Rick guess if Sam doesn't send anything over. If it sends one PCA, just one number, it reconstructs. That's what Rick will be able to reconstruct. If it sends two numbers, it can reconstruct this quality, so on and so forth. You can see how the face starts to emerge, starts to rotate from perfect symmetrical to a little bit turn, and more details emerge. In the end, it becomes this.
What's the relationship between the PCA and SVD? This kind of reminds me of SVD when you get 48, like this gauge, 48 singular values.
Yeah. PCA is the eigenvector of the covariance matrix. It's not the eigenvector of the data matrix X by itself. It's the covariance matrix. That's the eigenvectors of covariance matrix. It's really to capture the covariation pattern. See, it's the mean value is subtracted. It's only through the stack of images I analyze which direction has more variation.
This is technically the SVD of the mean image of all the stack.
I have a stack of images. First, I calculate the mean, and then I subtract the mean from each of these images. All I get is how each image is different from mean. So the absolute value doesn't really matter. And now I look through there's zero-centered, zero mean data. I calculate the covariance matrix. Okay, and then I calculate the eigenvector, and that's my PCA. But as I explained, in reality, you don't go by this routine because D is much greater than that. what I do is first, if I have 200 images, I calculate the grand matrix. It's 200 by 200 image similarity. I calculate the eigenvector there, and then I derive the eigenvector for the covariance matrix, as I explained earlier. It's just much more efficient. But it's equivalent. Conceptually, it's the eigenvector of covariance. In practice, though, you may run out of memory if you try to do that. Okay? Any questions? Okay. So how does PCA compress data? Pretty good compression there. You have SVD decomposition, the covariance matrix are written as such. If I take the first PCA and I reconstruct with it, the residual is essentially this, and it becomes the original data minus the reconstruction with the first PCA, essentially becomes this. This has sort of the SVD decomposition format, but SVD requires the singular values to be arranged in particular order from large to small. So I just reshuffle this, and S2 and SD pops up. It's like a bubble sort. They just move up, and the 0 comes to this. So you can think of, when I do, this gives another view why the sequential PCA seeking is equivalent to joint PCA seeking. Joint PCA seeking just seek the first, the first k leading eigenvectors, right? If I do sequentially, I first figure out the largest eigenvector, and then essentially the data I have is this, and then I can peel off the second one recursively. Okay? So this is this concludes the PCA. What you need to take away is the following. I have data. Think about Gaussian. Whenever you work with do PCA, you should think about it assumes the data is Gaussianly distributed. It may be off. Very important, you have to subtract the mean. It's going for the variance. It has to be centered. Think about this. If the data lies in this somewhere here, if you don't do that, it's essentially fitting data like this. This becomes your PCA. This has nothing to do with variation. Okay? And then after you do the mean, essentially you want to calculate these major axes and minuses of the data itself, which capture the spread of the data in the feature space. From Sam and Rick's point of view, I have an original image. I'm going to encode into this PCA coefficients. And that's, after I do the centering, I project to this PCA axis. This is a linear transformation. I send it over to Rick. Rick used this, use the PCA basis to reconstruct with these coefficients, then add the mean back. That's my reconstructed image. That's what I have shown with all these either progressive reconstruction or each image is reconstruction. This is a linear encoder-decoder pipeline. We can replace it with a nonlinear encoder-decoder. That's what deep learning does. Expand the power of that. Okay? Okay. So let's come back to regression. PCA only is unsupervised dimensionality reduction. It only concerns one data space X. Nowhere we are dealing with Y. It's not a regression formulation. I have a data, I want to reduce the dimensionality of X. And I think all the variations are important. I want to keep them. That's the idea of PCA. But let's look at the regression again. X and by D, Y is the target value I need to regress. Let's assume they have zero mean. So linear regression essentially is seeking the linear relationship between X and Y. This, I have hand-waved explaining the idea. Now, I made this diagram to illustrate SVD. Any matrix X can be decomposed into singular vectors U, S, V transpose. What does that mean? It means the following. The intuition is the following. Any matrix can be understood as a transformation, an action to be taken on any point in that space W. If this is n by d, by itself, you can understand by itself, but it's much more interesting to understand it through the action it takes on a point in the feature space. If I have any feature point W, how is this X going to act upon it? So this is my U S V transpose, act upon W. So if this is my W point, first V transpose W, so first of all, U and V comes in pairs, right? The first icon, so I color-coded is a consistency. If this is my first right icon singular vector, this is my left singular vector. There's no ambiguity, it's one-to-one. This is what I frequently referred as mode. This is mode in the input space, in the feature space. This is the corresponding mode in the output space, in the instance space, okay? And so they come in pairs. Anytime you give an X, it carries this intrinsic coordinate system, V and U. That's fixed. V1, just like eigenspace, eigenfaces. V1 correspond to the basic mode of oscillation. The next one corresponds to the second mode, okay? Just that, okay? These are two intrinsic coordinate systems. I mean, illustrated here is both 2D, but they can totally live in very different space. This could be a 500 dimension, this could be 1,000 dimensions. What matters is they correspond, okay? One-to-one mapping. So when I have a W, the action of X applied to W, first thing is to project onto this input space, because it's a proper coordinate system. I get a projection coefficient C1 and a C2. Yes? If the second one is do the scaling. I'm going to take C1, C2, I'm going to scale them accordingly. C1 is going to be scaled by S1, C1, and C2 is going to be scaled by S2. What's the output? I'm applying an action to a point in D-dimensional space, but I'm outputting a point in the N-dimensional space. It can be understood as using the rescaled coefficients to reconstruct this point in U. That's my output. Okay? To recap, any matrix N by D comes with it two coordinate systems, intrinsic. V and U, each is a orthonormal coordinate system. Any W, if it activates first mode by this much, C1, and the output N, it's the corresponding U vector, that mode will be activated. The size of activation is the same, is proportional C1, but scaled by the singular values. If singular values are all the same, then it just how much each mode is activated input side, how much mode at the output side is activated. Okay? Singular value is just to change, modify the strength of activation. Now we're going to take this view to look at the least square linear regression again. I have the linear regression goal. X act upon W, approaches Y as close as possible. Any least square solution can be understood, as this modification of the singular value of U and V for the data matrix. Okay, the left side, because this lives in the D by 1, it's in the V space, in the feature space. And this is just say the target value, how does it resonate with my intrinsic modes at the output end. That's what it is. So X2 eigenspace decide the structure of solution. You know, this decide the structure, no matter what W is. Why just go on for the ride? Really, it doesn't change the structure. It's just a linear projection. Okay? So first, let's look at pseudo-inverse. Pseudo-inverse, the solution, essentially, if I have USV transpose, and there's, this part is non-negative, then the rest is rank deficient, okay? And I expand it by SVD, and U is orthonormal. I can multiply this by both sides, so I have this cancels out because of orthonormal. And now I need to invert this side, but S, I cannot convert inverse like this. I'm going to take the pseudo-inverse. Pseudo-inverse just for those that, it's non-negative. Non-zero, I do the inverse. If it's zero, I make it a zero. That's pseudo-inverse, right? The minimum norm solution you have studied. Now this can be understood. You can see the structure remains, and what's this weight function? If S is greater than zero, it's the inverse. If it's zero, it's zero. PCA. I'm going to use PCA to my data X, right? PCA only handles single data set. It doesn't deal with Y, just X. I have a lot of dimensions. I thought I can do some feature selection. I'm going to use PCA to do feature selection. Okay? So what do? Instead of using the original X, I'm go for the PCA. I use the PCA reconstruction to represent my X. So essentially it's this. So I plug that in, and I can, I go for the pseudo inverse over this equation. I get this. So the PCA essentially, if I do it in the PCA fashion, the wave matrix essentially, if S is less than, if it's smaller than the kth eigenvalue, anything beyond this, k plus 1 and beyond, it's going to be 0 because it's all zeroed out. Otherwise, it's going to be 1 over S. Rigid regression. Rigid, again, I have this. This is my data X. Rigid regression, I go for the covariance, right? So I multiply X transpose X, and I get this. So I'm solving the the covariance added with this the prior term, and then I plug this into this, use SVD to represent the covariance matrix. Becomes this, and V can cancel out because they are it's orthonormal, and this is always full rank. So I can just totally, just go to the other side, okay? So this I can do the inverse, and this V transpose, it's orthonormal matrix, the inverse is just V, so I have this representation. And now this portion, again, it has the same structure. The ridge's weight function is essentially S over S squared plus lambda. Now, let's put them together. All the least square solution takes its form. All it does to modify the singular value. The singular vectors are intrinsic. Once you have the data matrix, there's nothing you can do. You can't touch that. The only thing you can transform is the singular values, and that's what it says. For P inverse, essentially, if it's 0, you ignore it. Otherwise, it's going to shoot up. If I have a small thing, it's a big pulse delta function, and all the way, it's a 1 over S function. But there's a big discontinuity at a 0. This can go on and on all the way up. And PCA is this red curve. The smaller value is going to be 0. Larger values, it's going to follow this curve, 1 over s. They converge to the same function. Okay, it's this function. You can think of original discontinuity of P inverse at this 0 point is mitigated. All the first segment of this is knocked out to 0, and this discontinuity is so much smaller. Ridge growth, I should try to do better, because after all, you still have a discontinuity. You try to smooth over between these two curves. It's 0, it's still 0. Otherwise, it gracefully, transition into this 1 over s function. When you do deep learning, you observe similar phenomena with early stopping. Okay, so you can understand the PCA essentially doing data regularization. You throw away some data, and the behavior is very similar. I think this is a proper time to stop. I want to take questions on this section, if you have any. Yes? TLS, the question was, what's the solution when using TLS when y is not a scalar, maybe have k dimensions? You tell me, what's your best guess? TLS for a single scalar, that would be the least eigenvector. Yes, it will be the k least eigenvectors. If it's 1, it's just the last one. If it's 2, the last 2. Okay? You can check out more derivation details at Wikipedia, but the idea is exactly the same. It's just a little bit more math. Any other questions? Okay. Oh, yes, there's a question in fact.
Is it possible to think about TLS as a decision framework?
TLS and PCA. PCA is TLS. The difference is, though, it's in the joint space SY. That's the only difference. Here, the reason I'm only compare them because they fall into the family, assuming X is noise-free. Okay? Other than that, if you treat S, Y as together, you're just fitting it, you get your TLS. Okay. I would like to start something on CCA. I want to use the time because if we cancel the class next time, it's a good connection to the next thing about CCA. When we learn regression, we have several scale issues. First, you have a lot of data. You have a record about some entity. Each dimension, what is a feature dimension? It could mean really different things like height, weight, blood pressure, right? These are different types of measurements. They are just stuck together as one record, okay? In reality, in practice, we are facing such an issue. It's a feature collection. They don't mean the same thing. It's not the same as images. In images, each dimension is a pixel, and the value, the range space is just the intensity, and at the different dimensions, at different pixel locations, they all mean the same thing. It's the amount of light hitting that pixel. They're comparable. But if you deal with heterogeneous features in the real data, you have this serious problem. How do you compare height versus weight? They're just numbers once you represent them. The second thing is feature engineering. Even though you're given these raw features, we have learned how to augment the power of regression by adding more features. We can add polynomial features, RBF features, or any nonlinear features. There's a question? Yeah.
What if we normalize all of that?
Yeah. Very good. I'm getting to it. Just okay. The third thing is a feature scaling. There are different units and weights of measurements. Today I represent the weights in terms of kilograms. Next day maybe pounds or maybe tons, you know. And that will make the numbers drastically different. If you do PCA, you know, you're gonna you're gonna get drastically different results. Okay, so we will get to how we usually deal with these issues in the next class. Okay, thank you guys.